2, 1. All right. Let's go ahead and pick up where we left off, where I pointed out that, as we noted at the very beginning of the course, the Riemann integral seems to have a bit of an issue, because when I create a certain sequence of functions, the limit doesn't behave nicely. So let's take some time here to formally set up how we're going to deal with sequences of functions, and equipped with this, we're going to then make the way towards fixing the Riemann integral. All right, so what do we mean by a sequence of functions? Okay, so for us, that's going to mean I've got a collection of functions indexed 1, 2, 3, so on and so forth, and they all share a common domain, and they all output to the real numbers. All right. The obvious thing that you would want to do with this is give meaning to the limit of a sequence of functions, right? I've got a sequence of numbers, I would like to get a limit for that, so sequences of functions, I would also like limits there to be meaningfully defined. And the obvious way to do this is, well, I know how a limit of a sequence should work, given my functions. Well, what's the key defining property of a function? Well, give it an input, you get an output. Well, if I give my sequences a fixed input, that will create a sequence. So for each input x, there is an associated sequence of real numbers, and naturally then I would like to investigate how this stuff would work. So basically anything that we previously defined for sequences, we can carefully bring that over to sequences of functions, right? Okay, so before we go in all guns blazing with limit, let's go ahead and recall that limits and boundedness were a connected idea. So let's talk about boundedness and sequences of functions. So there are two ways that a sequence can be bounded. So pointwise, meaning that the sequence of outputs is bounded for each particular input. Or uniformly bounded, meaning that my functions are all bounded above by a fixed quantity, and that's good across not only the sequence, but across all of the inputs. Okay. Now note, if you're uniformly bounded, you're obviously pointwise bounded. However, the converse is false, and here an example I think really drives home what's going on between the difference of these two. So pointwise bounded is each input, the associated sequence is bounded. Uniformly is no matter the input and no matter the function you're looking at, we're always bounded above by a single quantity. If I look at the collection of functions defined on the interval 0, 1 by 1 over n times x, well, for any fixed input x, the sequence is bounded above by 1 over n, because 1 over x, because 1 over n is just always making this smaller. As n increases, this gets smaller and smaller and smaller. So for any points, right, note, if you fix an x and you let n go to infinity, this goes to 0, right? So these sequences are bounded, right? In fact, there's a pointwise limit going on. All right, but across the board, note that for any input, there is an upper bound, but the upper bound's 1 over x, and as x gets really close to 0, that gets really big, so there can't be a single m that bounds all of these universally. And that's pretty easy to see from the graph, and here I made Copilot create a picture for me, because I wasn't going to actually sit down and do this. But here n equals 1 is my first 1 over x, n equals 2 is my 1 over 2x, then I've got my 1 over 3x, 1 over 4x, 1 over 5x. So note, as the n increases, it collapses down. However, the n's are never going to overpower the x's as you get close to 0. They're always going to blow off to infinity. So for any fixed point, if you were to fix a point, say a half, and you looked at all of the terms in your sequence of functions for that fixed input, well, obviously they're bounded. But as you let that input get closer and closer to 0, while they are all individually bounded, as you get closer to 0, that individual bound is going to have to get bigger and bigger and bigger, because the inputs are getting closer and closer to 0. Right. And this kind of here reveals the subtleties that you're going to have to be dealing with when you're working with sequences of functions. It's very natural to just focus in on one input and look at that sequence, right? Fix an input, then create the sequence using the functions, and that will give us information. However, we want to big picture things. So while pointwise stuff is going to work out nicely, we are also going to have to think about the sort of uniform quantity as well. And we'll get into that a little bit more deeply. But while we're talking bounded, note that pointwise bounded then means that these associated output sequences are bounded, which means I have access to supremums. Right, so given an input, this is a bounded sequence, so it has a sup. It has an inf, and also note that it's got a lim sup and a lim inf. So note the difference here. The lim sup, again, is the lim sup of the sequence. Here the sup is the supremum of all of the outputs. And note that these are connected to each other, because remember, lim sup is the sup of the infs, and lim inf is the sup of the infs. Right, in particular, right, the limit supremum of Fn is in fact the infimum of the G's, which are created by the supremums. Right, it's the inf of the sups that gives you the lim sup, and the sup of the infs gives you the lim inf. Right, so again, annoyingly, right, the lim sup is a limit of supremums, however, it's actually equal to an infimum. And similarly, the lim inf is a limit of infimums, but it is equal to a sup. And we'll exploit this in a little bit when we get into measurable functions. All right, cool. All right, good stuff. And speaking of doing things point-wise, I, of course, can talk about the pointwise limit. So indeed, we'll say a sequence converges pointwise to a function if at each input x it's equal to the limit of the sequence. Right, because if you lock down a point x and then look at the outputs for each function, that will create a sequence. And if that converges, you obviously have a limit. And this is all very natural. We converge pointwise if pointwise you're equal to your limits. And naturally, you would just call this thing the limit of f sub n, because what else would it be? All right. Now note, of course, that if you converge pointwise, that means each sequence generated for each input will be a bounded sequence and thus be pointwise bounded. However, you can be pointwise bounded and fail to converge pointwise. And again, it just comes from the fact that bounded sequences may not converge. They all have convergent subsequences, though, right? Oh, so you've got your lim inf and lim sup if you're pointwise bounded. However, we of course can recall that if you have a sequence that is monotone increasing and bounded, it converges to its sup, and likewise it will converge to its inf. So a sequence of functions will be said to be monotonically increasing if the associated sequences of real numbers are all monotone increasing for each input. Similarly, monotone decreasing is defined, and note that then a monotone increasing sequence of pointwise bounded functions will converge pointwise to their sup, and a decreasing bounded sequence will converge pointwise to its inf. All right, so no, we've just recontextualized a bunch of terminology that we already established for sequences to functions. All right, now we've finally formally gotten to what pointwise convergence will mean, but note we talked about this day one, and we pointed out that while pointwise convergence seems like the right idea, it kind of fails and falls short a lot of the times. And note, we already saw this kind of going on when we were looking at 1 over n times x, that sequence of functions. Pointwise, it's clearly bounded, because if you were to look at any individual vertical line, it's behaving. But if you look at all of the vertical lines of the big picture, things are not exactly as they should be. And a great example here to really hammer home that while pointwise convergence is in some sense right, it's gonna break things in ways we kind of don't expect. All right. So, for example, x to the n, I can look at the sequence of these functions, and if I look at them pointwise, well, right, each vertical line, things are collapsing down to 0, except at 1 when they're all equal to 1. So the pointwise limit of all of these xn's is this function, which is 0 everywhere except 1 when it's equal to 1. But each one of my f sub n's is continuous, but this pointwise limit failed to be continuous. And I don't like that. I really don't like that. Right? Continuity and limits should work together. That's the whole point of continuity, right? That's the whole point of defining limits from scratch and building them all up, right? I want the limit of continuous functions to remain continuous. However, here we see point-wise, that can't possibly be true. So I need to strengthen what we mean by limits of functions. All right. So I got to carefully examine what this statement really entails, and then see what we can do to fix it. All right. So indeed, if I have a sequence of functions and they converge pointwise, so note that this statement is given an x and an epsilon, there is an n, so things work. All right. So note this n is dependent on not just the epsilon, but also the x. So when we were talking continuity, we saw this issue already come up, and that's why we had to introduce this notion of uniform continuity to help us out. And so we will then upgrade pointwise convergence. Similarly, we'll say a sequence converges uniformly if the n is not dependent on the inputs. Right, similarly to how pointwise bounded we were, right, that works pointwise, but maybe it doesn't work across the board. So here we go, we want the convergence to work across the board. So we'll say a sequence converges uniformly. If given an epsilon, there is an n, so that we get within epsilon, and that's good not only for all n, but for all x. So again, the key difference here is the relationship of the for all inputs versus where there exists an n. Normal pointwise convergence, that n is dependent on not just the epsilon, but the point x that we're working at. So uniform convergence, similar to uniform continuity, right, we're going to want the n to be independent of the input x. All right, cool. And so equipped with this, let's go ahead and actually prove if you have a sequence of continuous functions that converge uniformly, then continuity is in fact preserved. All right, so given an epsilon, then, since we converge uniformly, that means there is an n, so that f sub n of x minus f of x is within epsilon over 3 for all n greater than n. And again, this works for all inputs. And this particular n gives me one of the fn's on my list, and that's continuous at a, which means there is a delta, so that f sub n of x minus f sub n of a is within epsilon over 3. So note the epsilon over 3, so it's probably going to be 3 things. So, that should be an a, not an x naught right there, and that is going to be an error that propagates, because I totally did not copy and paste this and half-assed fixing it. That's not what I did at all. All right, don't worry, I fix it. Okay, so for any x that's within delta of a, all right, well then, for any such x, if I look at f of x minus f of a, well, I can sneak in f sub n of x, there and there, and I can sneak in f sub n of a, there and there. By the uniform convergence, I know that this is going to get less than epsilon over 3. By the uniform convergence, this will get less than epsilon over 3. And by the continuity, the middle term gets less than epsilon over 3. And then there we go. The uniform limit of continuous functions remains continuous. Cool. All right. Now, it's worth noting historically, so the person who actually proved this literal proof that you are seeing in front of you with the 3 epsilons, our boy Cauchy figured this one out. He did it. He went, hey, limit of continuous functions is continuous. And he added the epsilons to prove it. But it's actually interesting. While Cauchy had this, he didn't have uniform continuity figured out. And so what he was attempting to claim that the pointwise limit of continuous functions is continuous, which is really weird. He wasn't catching the subtlety of what was going on. And other mathematicians knew this, that there was an issue with this sort of limit of functions of continuous functions may not be continuous. So they were pretty suspicious of what Cauchy was proving here and what he was claiming. And it wasn't until Weierstrass, like later in the 18th century, really figured out there's this uniform thing that's going on. Right, where there's this n that is independent of the inputs that you need to be careful of. But Cauchy had this proof. He figured it out. He didn't exactly have the uniform convergence thing figured out yet in his head. All right. Pretty cool. All right, so there you go. So pointwise is not necessarily going to give us continuity, but if we upgrade a little bit to uniform, then life is good. All right, great. Now, note here, if I had the target that I was aiming for, then I know that the target is continuous. So if I have a sequence of continuous functions and I know they converge uniformly, then I know the thing they converge uniformly to is continuous. But of course, that's not useful, right? Because I need to know what the function is beforehand. Naturally, I don't want to know it. And that's why, of course, since we're talking our boy Cauchy, we can talk about a sequence of functions being uniformly Cauchy, and note that this is basically, the sequence of functions. Their outputs are Cauchy sequences, right? And again, we need the uniformness for the Cauchy. Given an epsilon, there is an n, and that n is not dependent on the inputs. Cool. All right. And naturally now what we want to prove is that if you have a uniformly Cauchy sequence, then it converges uniformly to something, right? So the Cauchy completeness of the real line upgraded for sequences of functions. Cool stuff. Now, this one right here, this proof. There's a lot of proofs so far that we've done in this class that I really like, but this one... Oh, kids are yelling. I don't know if everybody... Yeah, right? That's a good time to cheer. This proof right here is very important to me. This is a proof that was like a big moment in my math life. Because it was really, once I had this proof figured out, once I really got all the juicy details under control, like it felt like like the floodgates open, like something unlocked in my head, and then all of a sudden I was just like a master of epsilons and deltas and capital N's, and like I knew how all this stuff worked, and this was the proof that got it for me. So this one, right, this is like the inflection point. Once I got this, then right, I was just zooming, man. I was epsilon and I was delta, and you couldn't stop me. All right, so let's see how this one goes. All right, so by hypothesis, since we have a uniformly Cauchy sequence, given an epsilon, there is an n, so that the outputs are all within epsilon of each other. That's good for any x, and any n and n bigger than n. So now in particular, this means that for each x, I have a Cauchy sequence of real numbers, and thus they are convergent. So I can create the pointwise limit. So I know that I have something I converge pointwise to, but I need to actually show that we converge uniformly to this thing. Right, so the proof's not over yet. And I remember the hint I actually got for, this was actually an exam problem that we had to do. And the professor just gave us the hint of, well, first prove pointwise, and then show that you have uniform. All right, so I got the pointwise part of it, so let me actually get the uniform part of it. And also, side note on all of this, if you do uniformly converge to something, you have to pointwise converge. So it's the jump from pointwise to uniform that requires a bit of work. All right, so let's get the uniform convergence. Given an epsilon, I want to show there's a capital N that works. All right, well, the Cauchiness gave me a capital N, and so let's, as always, epsilon over 2 that. Now, pick any point x out of E. I want to show that fn of x minus f of x gets less than epsilon. All right, so given epsilon, there is an n that works for all inputs, and we're happy. Now, because the sequence converges, there is an m, so that we get with an epsilon over 2. So pick the max of the two, as we always do, and now note here that for any n bigger than m, if I look at this difference, now note I want this less than epsilon, and right, that epsilon and this n were independent of the inputs x. The x is happening afterwards. But note, I'm using my x to find these j's. Pretty sneaky. So I sneak in the j. Now, the j note is dependent on the x, because this m that I got here came from the pointwise convergent, which is dependent on the x. However, right, the n here that we started with was only dependent on the epsilon. So I've snuck in a j that's dependent on the x's, and to make this less than epsilon over 2, and that less than epsilon over 2. And there we go. So, pretty cool, right? Once I saw how all of that worked, and paying attention to the dependence on things, right? This n came from the uniform convergence, which only depended on the epsilon. But then each x has a m that I can find, and I can then take the max of those. Now this j is dependent on the x, but I don't care because those j's are showing up once I've already got my n bigger than my capital N, which only depended on the epsilon. Really sweet. Really cool, I think. All right. Cool. All right, so there you go. If you've got uniform convergence, if you've got a uniformly Cauchy sequence, it uniformly converges to something. So note, any uniformly Cauchy sequence of continuous functions will converge uniformly to a continuous function. Pretty cool. All right, well, we were just talking integrals. So let's show that Riemann integration is actually pretty okay if you uniformly approach it. Okay. So now we see that Riemann integration, while it is very nice, requires this little extra strength convergence to make the integrals work the way you want them to work. If you converge uniformly, then the limit can get pulled in. But we already know from day one in the class you can't pull in the pointwise limit. So while uniform convergence in some way will fix the issue, there's still this sort of, but the pointwise limit is still like the real limit. You're just sometimes asking the limit to be stronger. So we're going to use that as sort of our baseline of, if we're going to find something that's going to fix it, it's going to have to respect pointwise convergence. But that's for the next video, and before we get there, let's show that the Riemann integral is pretty okay with uniform convergence. Okay. All right, and again, note. So, again, our plan moving forward then, if we're going to fix the Riemann integral, is we have to build up a theory for integration where we keep pointwise in mind rather than requiring this stronger uniform convergence. All right. Okay, so let's do it. So if we converge uniformly, given an epsilon, there is an n, so that for all x, life is good, and here I'm bounding it by some epsilon over some junk, and the I need this junk to make it work will become apparent later on. Okay. So note that for any partition, then, if we look at the upper Darboux sum of f minus f sub capital N, all right, well, these will then be rigged to get less than epsilon over 3 because I rigged the outputs to behave nicely. And similarly, the lower Darboux sums, I don't know where this alpha came from. Again, well, I know where that, man, that, oh my god, that alpha has survived a lot of copy pastas there. Man, I can't believe that alpha is there. So that alpha is coming from, yeah, this is a fun little thing. That alpha is coming from my notes on this from 2013 when I was teaching the equivalent of this class at Iowa State. And we weren't doing the Riemann integral there. We were doing what's called the Riemann-Stieltjes integral. And there's like a gauge alpha that pops up. Oh man, I can't believe that survived that long. Well, it's dead now. Anyway, so the upper sum of f minus capital Fn gets less than epsilon. The lower sum gets bigger than epsilon over 3. So, hey, it's integrable. That means there's a partition where we're racking up these things less than epsilon over 3. All right, and since f is equal to f minus f sub n plus f sub n, then when I look at this partition of f, okay, well, it'll be less than or equal to the sum of the two by the triangle inequality, and a similar thing over here. The lower sum splits up nicely. And now when I go ahead and look at the upper and lower Darboux sum of f on these partitions epsilon. All right, these will get trapped between the difference there and the difference here, and each one of these things is going to be rigged to get us less than epsilon over 3. Right, indeed, this portion right there, which is this one right here, is less than epsilon over 3, and as we already rigged, this one is less than epsilon over 3, this one is less than epsilon over 3 as well. That was the things we did on the previous slide, and they all add up to epsilon. So note now that we've demonstrated that given an epsilon, there is a partition, so that my function f's upper and lower Darboux sums are within epsilon of each other, thus ensuring that it's Riemann integrable. So a uniform limit of the Riemann integrable functions remains Riemann integrable. Now let's go ahead and prove that the limit of the integrals is also what I want it to be. Alright, so let's define I sub n to be the Riemann integral of each sequential term in my sequence of functions, and we'll let I be the Riemann integral, which we know to exist. Alright. So, given an epsilon, since we have uniform convergence, we know that these will get with an epsilon over b minus a, and that's good for all n greater than n. And now when I look at I sub n minus that, okay, well, the Riemann integral is linear, so when I take the difference, I can pull out the integral and take the difference of the functions. We know the absolute value of a integral is less than or equal to the integral of the absolute value. These are all bounded above by that, which means that this integral is bounded above by this times the length of the interval, which was rigged so that we get epsilon. And hey, given an epsilon, there is an n, so this gets greater within I for n greater than n. So indeed, it converges where we want it to. And there we go. Great. So we have now proven that Riemann integration likes uniform convergence. So if we're going to build a new theory of integration, we're going to have to keep things pointwise in mind. So when we start building up things, we really need a collection of things that's going to behave pointwise, right? Because pointwise Riemann is not going to work. So when we create functions and we want to then integrate them, we want to keep this pointwise thing in mind. If we can create a type of function so that pointwise limits are behaving, then we've probably got a theory of integration that will be a little bit more robust at our fingertips. Excuse me. All right, and that'll be the plan for the next few videos.